Well, thank you for coming out tonight, and I hope that what I give you gives you a kind of a taste for what R can do for you, and in addition, maybe get you over that first stepping stone of things. The first part of tonight is going to be doing a seminar, so I'm going to talk through what R can do, demonstrate some of his capabilities, but then at the end, once I'm done talking and you've had a chance to ask any questions you would like, if you have brought your laptop with you and you would like to install R and work through getting things up and going, I will be here to help you with that. So our goal with the seminar series is not just to do a bunch of talking, but it's to help facilitate you in getting started with data science. And that means you need to get over that barrier of getting software installed, going through the first initial steps of getting used to it so that it's not a big unknown. And then once you've gotten used to it and you see what you can do with your own laptop or your own system, then that's going to help you start playing with it. And that's where you're really going to learn how to do this stuff. So, a couple of things to note here. We're going to open with prayer. And I think we need to keep in memory, or in light of what happened in Las Vegas. It's such a terrible tragedy. I think my wife texted me and says that I think this counts as the largest death toll in the nation. And I don't think it's just in recent era. It's, but let's see, there's 500 and some that were injured, and over 50 that have been killed. So, let's pray. Dear Lord, we come to you with heavy hearts, knowing that the state of our country is such that we see these tragedies happening with increasing frequency. I pray that you would give wisdom to the law enforcement officials as they track down what actually happened, and whether there are some other things that would tip them off to incidences like this in the future. But there are families grieving with loved ones that they've lost, family members, friends. I pray that they would seek comfort in you and not in other things. Give wisdom to Christians in the area, and as they would step in to be able to see how they can meet the need, that you give them a caring heart, a discerning heart, and a sympathetic heart, and that it would demonstrate very clearly your love to everyone in this world, and that you desire that all would come to repentance and know you as Savior. And I pray now as we go through the material tonight that you help me to speak clearly, that each one here would get a good sense as to what this software can do for them, and that it would take them one step further in their pursuit of understanding data science. In Jesus' name I pray, amen. Well, let's start off just a little introduction here. I'm going to use a few slides we had last time. What is data science? Data science, also known as data-driven science, is an interdisciplinary field about scientific methods, processes, and systems to extract knowledge or insights from data in various forms, either structured or unstructured, similar to data mining, and that just comes directly from Wikipedia definition. The key word in data science is not data, but it is science. Jeff Leake wrote an article with regards to that. The point he makes is that analytics, data mining, neural nets are just tools for managing and exploring big data. And the big data that is out there is, I think probably sometime in the future, we will try delineating some of the big data sources that we're aware of, but that's not the purpose for tonight's talk. Some interesting questions to answer. There's a trap in focusing on a collection of techniques or tools. You can get so enamored with what neural nets can do that you play around with the neural net and you never really do any real science. That would be one of the traps that we'd like you to avoid. The goal is to extract better understanding of the system. Data science has a goal of understanding, not just pretty pictures. And then these techniques can be used to engineer solutions. And I think I made a comment last time that the whole goal of data science is to use big data, bring statistics and computers together to somehow come to some actionable decisions based on the information that you've accrued. What does data scientists do? There was a TED Talk, and I don't think I have the reference here, but you probably do a search on most important skills of data scientists, and the summary is that people want answers in days rather than months. Exploratory analysis and rapid iteration. So if you're going to really explore things, you need to be able to try something out, see what the results are, try something else out to explore your data. Therefore, visual representation is there to enhance your insights, and you want to turn that data into actionable insight. And this is from a textbook or a book written that I'll allude to later, R for data scientist. And his view is that you use some techniques to import your data into a usable form. You tidy it up or you put it into a proper format, and then you go through this exploration phase, which is visualizing your data, proposing a model, transforming the data into a different form that might elucidate other features that are available, and then finally, when you get a good sense of your data, then how do I communicate my results? And then there are tools galore out there. Probably the two most popular languages available for doing data science is R and Python. And between those two, they probably capture at least 60% or 60 to 70% of what data scientists use for doing data exploration. But you can do data science with SAS, with SPSS. As Tim Twinstra does, he uses MATLAB. So you're not limited in your tools, but we're going to focus in on this tool tonight. And then, again, just so that you have a context of what we're trying to accomplish here, we want to do a monthly meeting. I think we're going to stick with the Monday evening. That seems to at least open up the opportunity for a number of people to attend. We want a presentation of a concept and or tool with some examples, and then do a workshop to assist you in recreating the examples. And so that's going to be the format I'm going to follow tonight. I'm going to go through a presentation and then help to facilitate you, if you want to stick around, to actually use some of the things that I talked about. To gain, or I should say to probably get a good appreciation of what we're trying to accomplish here, you should have a basic understanding of statistics. We're not expecting an in-depth understanding, but some basic ideas are going to be useful, and then some basic programming skills, because all of these things that we're going to go through are platforms that involve some level of programming. Possible topics, using R for data science, that's tonight, but in the future we do want to look at SQL and how you can retrieve data and put it into usable form. Probably look at something that helps you to look at text-based as opposed to just numerically based data. Geospatial analysis, and Mark Gaffney has got some expertise in that area. Pattern recognition, Tim Twinstra also has expertise there. Neural networks and data visualization. In fact, at this point, I probably need to do the introductions for those that have are kind of our core group for data science. Myself, Steve Gollmer, I have a background, actually my degree is in atmospheric science, so I do some work with satellite imagery, climate modeling, but I've used large data in a lot of different contexts and been using R lately. Tim Twinstra, electrical engineer, has been doing stuff with regards to image processing, looking for patterns and identifying features. John Delano is in the business department, primarily all the IT type of classes. And, excuse me, I think you said that your area was not aesthetic, what's the word I'm looking for taking commentaries from reviews and then getting a sense of what the review is really telling you.
Right, so like sentiment analysis.
Sentiment analysis, okay, what people's sentiment is about a product. And then Mark Gaffney over here, he does a lot of work with GIS, Geographical Information Systems, and geospatial data use. And then we have Ashley Holland, and her expertise is econometrics. Is that correct?
Yeah, that's right.
And that's kind of been the group of five that has gotten together and has thought through some of these issues, and so this is where we are going forward. Now there's two links I have here, and I want you to be aware of them. The first link is a Google site, and the Google site should look something like the following. And we have some documents available, discussion, but if you go to the documents area, the goal is to put the presentations here and make them available to you. At least I think right now, as people have tried to access them, I get a email saying, can I give them permission to do that? And that's fine, I'll just give you permission so you can get access to them. Because I wanted things to be a little bit timely tonight, in case you wanted to get access to some stuff, I set up a web page. And it's people.cedarville.edu, employee Gollmer S, and then datascienceindex.htm. And I have several links there. If you want to access last month's presentation, you can click here. If you want to see tonight's presentation as I go through it and you want it on your laptop, you can click here. And then to get to the Google site, I have a link there. I also have a link to CRAN, which is where a lot of the R software is available. And then I have something else called Physics Team, and specifically the link to software. I have some instructions on how to install Octave, but then I also have instructions on how to install R available. And then analysis skills, I just have some examples of using R to make 2D plots, using R to make 3D plots, using R to find solutions to multiple equations, multiple unknowns, multiple linear equations, using R to do linear fit of noisy data. So I have several different examples of different types of skills that might be useful for you to look and see what my code snippets look like and what the results are with R. So let's see, I've talked about that. So let's jump back to the presentation. So there's the address where I have several of those links if you need that. So this man right here, Bob Schumacher, we know him well, at least some of us do. For most of you, he retired about 4 years ago. And he was a retired lieutenant colonel in the Air Force. His research area, or I should say his degree, was in operations research, but he was a faculty member here the year before I came. And when I came, he was teaching physics. After I came, I took the physics, but he still was involved in the physics program. He also taught a lot of mathematics, but he was instrumental in getting the computer science program started here at Cedarville. He has two loves in the area of his research area is LaTeX and R. And so if anybody has credit for R existing on this campus, it is Bob Schumacher. He's currently retired. He's living over in Indiana. And in fact, one of his ministries that he really loves is he's involved in Gideon's International, handing out New Testaments on college campuses in various venues, but he's very active in the Gideon's organization. Now, in light of this, I would like to take a picture of you and send it to Bob Schumacher so you can see how many people actually came to hear a talk on R. Is that acceptable to you? I think you will appreciate the sense of the moment. There's so many of you can't fit them in. And a little higher. There we go. I think he'll enjoy that. In fact, our department has a breakfast every year. This is from a breakfast from probably about 3 years ago. But at the breakfast, invariably, the conversation always turns to LaTeX and always turns to R in some form or another. He's retired, but he hasn't lost his interest. So, Tale of Two Languages. Dickens, it was the best of times, it was the worst of times. Which is the opening phrase in which book? Tale of Two Cities. What are the two cities? London and Paris. Well, in this case, we're going to talk about the Tale of Two Languages. The two languages are Lisp and S. Now, Lisp ends up by developing or having a subcategory which is called Scheme, and it's a combination of Scheme and S that is the parentage of R. So let's look at Lisp first. Lisp stands for Lisp Processor. It's based on a paper that was written by John McCarthy in 1958. And the title of the paper was Recursive Functions of Symbolic Expressions and Their Computation by Machines. And a number of individuals implemented what he had expressed in this paper, and there were lots of different versions of Lisp. So by the time he got to 1981, there was a desire to come up with a common standard amongst all the Lisp interpreters out there, and it was called Common Lisp. There was another group out there that really wanted to simplify all of Lisp down to a common core, and they used what were called the Lambda papers to somewhat direct their vision, and as a result, they developed what was called Scheme. Lisp is a functional programming language. The idea behind it is that you treat computation like evaluating mathematical functions. You avoid mutable data. Mutable means changeable. You don't want any changeable data, and you want to avoid changing states. As a result, you can ensure reproducibility in your results. So if you run the program the first time or the 18th time, you get the exact same results. In contrast to functional programming is what's called imperative programming, and Fortran, C, BASIC, etc. all allow you to easily change the value of a particular variable. When you're doing functional programming, if you're really doing it the right way, you send stuff into a program, it passes back results, but those new results do not get attributed to the same variable. So you have this flow of how things are progressing, again, treating it more like a mathematical function in progression, so that the functions actually transmute or modify the data without necessarily going backwards and changing things in the flow of the data. There's something called lexical scoping. And lexical scoping has the idea that a variable name is determined by its local environment. Now, for any that have done any kind of programming, you have some global variables, you can have some local variables, and then you could call subroutines that have variables defined inside. It ends up that if you do not have lexical scoping, it's very hard to determine who is defining my variable. So if I'm defining a loop with I in it, does I have the same definition out here as it does here, as it does here? And if it's different, is there a way I can, just by looking at the code, determine how is I being used? And if you obey lexical scoping, it makes it very clear from the structure, the static text of the program, what's actually going on. Again, this really helps back with the idea of things being somewhat, where's the term I'm looking for? Reproducibility. That's really the key here. And then it was Scheme that incorporated lexical scoping into its version of Lisp. So Lisp basics. The main data structure is linked list. So think of a linked list as a pair of values. The first is my data, the second is a link to the next set of data. And then that next set of data consists of a value plus a link to the next one, and as a result, you can traverse your links to do operations on your data. Now you could think of this like a vector, but again, you're just linking data values together. The functional call for Lisp consists of parentheses. Inside the parentheses, you have an actual function or an operation. You then have arguments that that operation works on. Here's an example of defining the factorial function. First of all, the function is a definition function. The first argument is something called factorial, and now you have additional arguments that allow you to define this. The next time around, you could run parenthesis factorial, put in your number, and the n would be your second, or I should say factorial would be your function, and then n would be your argument, and it would pass back this iterative process and spit out your factorial of 15 or whatever number you put in. Because as you look at the structure, the reason I did this was, notice you get a lot of parentheses. John Delano talks about having done Lisp programming and really hating the parentheses. So I came across this cartoon on the net. Lisp is over half a century old. In fact, Lisp and Fortran were developed about within 1 year of each other. So they are probably the two oldest languages out there that are still used in a common form. But Lisp is over half a century old, and it still has the perfect timeless air about it. I wonder if the cycles will continue forever. A few coders from each new generation rediscover the Lisp arts. And then this individual comes in and says, these are your father's parentheses, elegant weapons for a more civilized age. So hopefully you catch the Star Wars reference. So that's Lisp. The other language is S. S is, and the problem with S is there's something called S plus out there, but it was quite a ways down the road. There's really not a nice pretty icon for it. There's not even really a name for it. But it's a statistical computing system. When S was first developed, they did consider an acronym which was going to end up by being SAS, but that one was already taken. So the primary developer was at Bell Labs, John Chambers, 1975. He initially used Fortran subroutine packages for graphics, etc. On the second version, it was ported to Unix, and by the third version, it was transformed into C as being the base code behind it, and allowed the language to become a bit more object-based in its structure. The goals of S was to emphasize an interactive environment. As a result, you can do very rapid prototyping. Put a command in, you see the results, you can transform, and again, using some kind of graphing capabilities, you could visualize your data as well as do statistics on your data. The goal is not only an interactive environment, but then also whatever interactions you do could also be reproduced as a programming language itself. You could write a script, run the script, and get the same things that you did as an interactive program. So now we're up to R. R was developed by Ross Ihapka and Robert Gentleman, 1992. They took an implementation of S and they incorporated some inspiration from Scheme. It's really a chimera language, which means it's both a functional language and it is an imperative language. And when you do that, that means you can really do bad, ugly stuff in R. Or if you try to obey the functional side of things, you can do some very elegant things in R. It all depends on what aspect or what side of the language that you really pursue. A clean program, or I should say clean functions, are functional programming. They take arguments, return values, and have no side effects. So I put stuff in, I get a result back, and it's like a black box, but I don't worry about it somehow changing the state of my machine and affecting my results. The functions are treated as a data type themselves. So data and functions are interchangeable, but you have to use them in the right context. Data flow is through a process of functions, and the program flow and data definitions are clear, or I should say the program flow and data definitions are clear because this code is static. It's not dynamic. It doesn't somehow rewrite itself. Object-oriented lets you swap things in and out, and if you don't know how things are swapped in and out, it makes things very dynamic and unpredictable. Imperative programming are the dirty functions. Usually R uses imperative programming to change global states of how you're running the program, as well as performing input-output functions. And as a result, with imperative programming, your data is mutable, and it breaks the reproducibility paradigm. Some issues here. Everything in R is a function call. R may appear slow if vector functions are improperly used. R inherently is vector-based. As a result, if you start calling loops to do calculations, you're going to find it's going to be very slow. But if you consider the thing as being a vector, it's one command without a loop, and it happens very quickly. Also, recursion is not very well implemented in R, and essentially Scheme and Lisp tend to be very strongly based on recursion. R does not implement the recursion very well at all. So here's the syntax. It looks somewhat Lisp-like, but instead of having the function inside the parentheses, you put the name of the function outside the parentheses, and you put all your arguments within, which looks a lot more familiar to how we normally do our programming in C and other languages. If you have a comment statement, you start with a pound sign, and then the assignment statement, normally we like to think of it as an equals, but preferably it is a less than dash combination. It's an assignment. It's equivalent to saying assign A the value of 4 plus 5. Equals can be used, but they're not allowed in control structures. The reason why is it was felt that equals lots of times gets mistaken with double equals, which is a logical comparison, and they don't want you to confuse equals with equals. So they discourage that. If you're really wanting to think in terms of the Lisp paradigm, here's your function is the assignment. You're assigning A, and this argument by this assignment, so A gets set to this, but this is another function call, which is a summation function, which operates on these two values. So this summation adds these together gives me 9, this assignment assigns 9 to A, and the return value would be A equals 9. Now, we don't look at it this way, we write it this way. Strings, usually double quotes are preferred, but you can use single hashes to indicate string structures. Backslashes are handled with special characters. So if you want to put, if you actually want an equal, or I should say a quote inside of a text string, you can do a backslash and then put the double quote there and have it not be interpreted as being the end of a string structure or the start of a string structure. A couple other commands here. It ends up that I want to make a list because Lisp is linked list based. So if I'm going to construct a collection here or a set of values, I can do C, and then my values are whatever I want to string together separated by commas. So by doing this operation right here, I've assigned to a vector of 4 values, but the vector is inhomogeneous. I could have integers, I could have floating points, I could have text strings, and I could also have logical operands inside, or logical states in there. And if you take a variable that's already been defined in R, and you just type that variable in and enter, it will print out the values of that particular variable that you have just typed. If I want to have a sequence of numbers, instead of writing 1, 2, 3, 4, I can use 1:8, and it will give me a sequential numbers from 1 to 8. And if I were to just make this assignment a collection of 1 to 8, typing B, notice I'm going to get my 1 through 8s. If I want to make an array, a 2-dimensional array, I could go, let's say in this case, 1 to 20. The dimensions of my array are going to be 4 by 5. And if I run that, this is the result I get. Now notice how my numbers are arranged in the array here. It's not 1, 2, 3, 4, 5. It's 1, 2, 3, 4, 5, 6, 7, 8, etc. You have to realize that R is thinking in terms of data it's going to do statistics on. And so this would maybe be my first factor, this could be my second factor, this could be my third factor, etc. And so you think of a particular variable, and these are the values that are assigned to that particular variable. If I want to extract, let's say, the third element of A, I just put a square brackets, put the number of the value in, and I get the third value back. I could do a 2-dimensional array, 3, 4. 3, 4 is going to give me 1, 2, 3, 1, 2, 3, oh, do it backwards, 1, 2, 3, 4, and gives me the 15. If you do a 2D array and you do not define one of the variables, or I should say one of the indices, and you just do the first indice, comma, it's going to return that particular row. If I do comma 3, it's going to return that particular column of data. So what would the following do? Now I gave you the answer. I was thinking of trying to set this up to reveal, but I think to just keep things moving here. If I do C1:5, this is going to give me a string of numbers 1 to 5. But if I want to have half values, I just divide this string of numbers, or this array of numbers, by 2, and I get 1/2, 1, 1.5, etc. Notice I don't have to take the first element divided by 2, the second element divided by 2, the third element divided by 2. The 2 division is going to apply to every single element in the array. If I want to add 4 to my array, notice A plus 4 is going to take this result and add 4 to each value. I don't have to do a loop. And then if I do A plus B, again, it's going to do a pairwise. So this element, this plus this equals this plus this is this, etc. Now, I threw in something odd here. If I did just A star B, what I would get is 0.5 times 4.5, and it would give me some value. I'd have 1 times 5 give me 5, and I could work my way through, and I would have an answer to this, which would consist of 5 elements. But if I use this particular notation, this is an inner product. So with an inner product, it's this times this, plus this times this, plus this times this, plus this times this, plus this times this, and returns the value of 43.75. Do not confuse the dash. That's just my PowerPoint notation of I'm the subpoint. Does that make sense? on how it's structured. Some more tasks. If you're doing any kind of programming, you need to be able to do assignments. You need to be able to call functions. You need to be able to do conditionals. So if else is structured this way, it looks very C-like in its appearance. It uses the curly brackets, but you do not have to worry about the semicolon at the end of each line. The new line is automatically interpreted as a new line without any extra symbols. If you want to do loops, a for loop looks like the following. Notice in this case, you have your variable that you're doing the looping on. The variable is in the following array, and notice this has defined an array. The array goes from 1 to whatever the length of my vector A is. And then I go through loop, and then I can maybe plot points, etc. If I wanted to do a while system, I can put a conditional here, and once again, it will just continue to loop through. So this aspect looks very C-like, which goes back to the roots of being part of S. So S was gone from Fortran into a more of a C structure. So the language looks C-like, except for the assignment statements. Get away from the equals and use the assignment statement. How do I import data? One of the most important data structures in there is called a data frame, and think of a data frame as a table with labels at the top. Now, for those that have had Gen Physics 2 with me, we do a nonlinear curve fit, and I have you use R in there, and this is one of those data sets. You're looking at the frequency of, that was set during the experiment, and those are the different majored frequencies. This was the associated response for different frequencies, both with a core and without a core, and this was for a LRC circuit. And then I have to import this data, and the way you import this data, you give a file name of whatever this file is, read CSV. CSV stands for comma separated values, and then it generates a data frame. And the data frame would consist of 3 columns, a label, and then data. Label, data, label, data. On the other hand, if I wanted to do a white separated variable, I could use a read table statement. Again, I could put the file name. If there's a header, I could put in true. If there is no header, I could declare false and assign it to my variable A, or my value A. But once the data is in there, how do I extract it from a data table? It's a little bit different than when you're doing vector assignments. With vector assignments, we just use the square brackets. But if it's in a data table, I have to define my variable, a $sign, and then whatever the label is for that particular column. So if I wanted to return all of these values, I would do a $frequency, or freak. If I wanted to pull off this value right here, I would do a $freak square bracket 3 close square bracket to pull off that specific value. Now it ends up that if something is inside a data table, it's not always convenient putting these extra $signs in. So what you can do is you can expose the data through using an attach statement. The attach statement would then, if I do attach A, I would now have a new variable in my environment that is labeled frequency, another variable in my environment labeled no core, another variable in my environment called with core, and then I could access frequency by just doing FREQ, open bracket, 3, close bracket to pull off that value. Then once you're done using those particular values and you want to hide them again, then you can do a detach, and now it's hidden back inside of the data table. So here's, yes?
Does the file name have to be, is file to be in the same directory?
It ends up, it depends on what you're using, but usually you want to be in a particular working directory. In fact, you do have to set a working directory for R to work. So if you have a script and you're running a script, you could either hardwire the address to a very specific directory, or you could define a working directory, and then it's going to look to that working directory, look for your file. If it can't find it, it's going to return an error.
Very cool.
So how do I get to R? First of all, I go to a location called rproject.org. Now, you have to choose CRAN, or actually this site is called CRAN, but CRAN is going to force you to choose a location from which to download your data. Now, the one I tended to use in the past was Washington University, but in recent years, Wright State also acts as a CRAN site for our project. So you can go to Wright State's website and with the right address, you can pull off all the R code that you need. This works on Linux, Mac OS, and Windows, pre-compiled. But if you want to do something really weird on a different platform, you can download the source code because this is open source. And that's the strength of R, is there's no fee for it, it's open source, and it's maintained. A new version is put out every year. There are incremental bug fixes and tweaks along the way during the year, but every year they do a full refresh on the code and release it. Now there are two different GUIs out there for addressing or working with R. The default one is called R GUI. It consists of a console. The console is where you're going to put in your commands and see the results of your commands. You can also open up a script window and write your script out and then execute the script. The results of the script will show up in the console, but you can also have a graphic window that will pop up and allow you to plot graphics. Once the graphics window is up, you can right-click on it and save it as a BMP or as a meta file and use it elsewhere. Also, it ends up that if you go through the menu items, this particular menu item is associated with this particular window, but if I were to click on the console window, the menu dynamically changes, and there's one called Help, and it has a number of different manuals that are accessed, so you can just drop the Help down, look and find a particular manual, click on it, and it brings up the documentation. You can also access documentation within R by typing help, parenthesis, quote, and then whatever function that you're looking for inside the environment. There's another one out there called RStudio, and there's been a lot of development done on this particular platform. It consists of, again, a place for your script to be developed. You can have multiple scripts open here. In the other one, you would actually have the multiple windows of different scripts that are overlapping. Here, they just use a tab system. You have your workspace, which is going to expose your different variables. So in RStudio, it's very easy to scroll through and see what the values are for different states. If you were to do that in RGUI, you have to type A, enter, and then it displays a list of the variable, or I should say the assignment for that particular variable. Once again, you have a console area that tells you the results of the program, and then there's a third area here where you can do help, or have your files, or any of your plots, and also look at what packages are installed currently. RStudio can be found at rstudio.com. It is, actually they have an open source version, they also have a professional version. Of course, the professional version is going to have much greater capabilities, but the open source or the free version is also very, very useful. And it's not really hampered that much between the professional version. It ends up that you can run R through a web browser using RStudio, and I think that's one of the additional bonuses with the professional version of RStudio. So you have four platforms. You have Windows, you have Linux, you have Apple OS X, but also you can do web browser. Now, packages. If you go to the CRAN site and click on packages, you'll get a long list here. Currently, there are 11,533 packages that are available from R. These are independently developed. They are put up there by independent programmers. You could write your own R package and submit it, but there are also some companies like RStudio that have contributed a number of functions or packages to R. You can find some related projects at this location here, and one area is bioinformatics. So there's a group that specifically is interested in bioinformatics and has developed code for that. You can go to their website or their link there and find out what types of things or how they're approaching the application of R. You also have spatial statistics, and again, it's a special group that would allow you to access that information. Because it's easy to get lost amongst 11,000 plus packages. And so if you have a core set of packages that you know work well together, that's always a bonus. Installing a package. If you're in the R GUI and you're at the main console, here's your menu items. Notice there's that help menu, but another one is packages. Now when you install packages, there's several ways you can do that. You could go directly to the CRAN site, download a zip file of that particular package, And then by going to a location on your hard drive, you could install that particular package. It ends up that when they update packages, then you have to keep downloading, updating, downloading, updating. Another option is to first of all select a CRAN mirror, which would be the right state site or whatever one you prefer, and then click on install packages, and then it'll give you a list of all 11,500 packages that you can click on and install. So either download the zip file or go directly from CRAN. R is updated annually, as I mentioned already, but whenever there's an annual update, your packages usually get updated too, and if they're out of sync, R will usually request that you download the most recent package, again, so that it avoids any kind of bad behavior. So how do I do graphics? The default graphics in R are what are called lattice graphics. Primarily, it's a coordinate system where you can draw rectangles, frames, labels, and draw all of your graphics out in that fashion. There's another group out there that is developing what is called grammar of graphics. It's based on a paper by Wilkinson from 2005. And grammar of graphics would say, instead of thinking in terms of drawing a plot out here, what if I were to break up graphics into semantic components? So when I'm doing graphics, first of all, maybe I have multiple layers that I want to lay on top of each other. There may be certain geometries that I want to modify before I plot my data. There are certain aesthetics, colors, shapes of your markers, whether it's triangles or stars, etc. Facets, maybe I want to have multiple panels put together. All of those are treated in a very consistent fashion, and then all of a sudden it starts looking like Linux, where if you're doing any kind of piping, I do this function, I pipe it into this function, this function, this function, and it essentially builds up my whole graphic display, or I should say my visual display, overlaying multiple features on the same graph. If you want to see what graphics capabilities there are, there's an rgraphgallery.com, and you can see what types of things are available for lattice graphics as well as for ggplot2. And Hadley Wickham was instrumental in getting ggplot2. I will, again, probably allude to him also. Now, instead of going out to the net and pulling a bunch of nice pictures that other people have generated, these are ones that I've generated for work I've done. I did some work with climate modeling, and in order to put together a presentation, I had to do I wanted to actually make a movie loop of the climate results over time. And the package, if I don't use a nice systematic package, you're doing this stuff by hand over and over again. So I wrote up a script in R, and this is just one clip of a movie loop that I generated. I also did some nonlinear dynamics. So this is a phase plot, and then the phase plot showing a trajectory. I could also show a three-dimensional vision of that same trajectory as you're going around the phase plot. And then I was using some satellite data. I did some cluster analysis, and then the cluster analysis attributed to the image itself. And I think I showed this picture last time, where you can see snow, clouds, etc. from the classification scheme. So that just gives you a very short or small sampling of what graphics are available. There's something called rattle, and this is what I want you to maybe see as the first step into R. Rattle like a baby rattle. The goal is to make data science in R as simple as possible. So you bring up Rattle. It's a package that operates within R. You can then load in your data set, and then it has a number of options available. You can load the data, you can explore the data, you can transform the data, you can do cluster analysis, you can model it, you could then evaluate your models, and it's got neural nets, it's got all different packages already incorporated here, and it's pretty much click and look at the results. And then, nice thing about Rattle is you might do a lot of this interactive clicking and working with your data, but eventually you'd like to be able to write the script for R that goes with that. As you're doing any motions here, it logs your results, and you will see it in readable R code, which means that once you've done a certain segment, you can take this code, write it off as a separate script and incorporate it into maybe some other work that you're doing. Rattle continued, so here's an example. You load in some data. I reduce the data down into a max temperature, a temperature at 3 p.m., sunshine, pressure at 9 a.m., and pressure at 3 p.m. The whole goal is, can I predict whether it's going to rain tomorrow or not? And so this particular data set has all these statistics, and then if you do a correlation of the data, it can generate a correlation plot where the blue dots are big and round. That means there's a positive correlation and a very strong correlation. And notice on the diagonal, everything's going to be 1. But this one right here comes out to be 0.969, so a very high correlation. Other regions where there's very weak correlation, like the third entry, this is negative 0.068. And then if there's a anti-correlation or negative correlation over here with max temperature or min temperature with pressure at 3 p.m., notice this is going to be negative 0.529. So just an example of some things that you can do very quickly with Rattle, get a visual result, and then move on. Because again, think back when S was started. The idea was to be able to very rapidly work through data, visualize it, get a sense of it, so that you could get usable results. And Rattle is trying to even make it easier than that. Now, I mentioned the fact that you have this huge raft or palette of packages to work from. How do I decide which ones work well and play well together? RStudio, or the group from RStudio, has laboriously put together a consistent set of packages. They call it Tidyverse. It's a collection of our packages. They share an underlying philosophy and common APIs. These are the main components of Tidyverse. You have DPLR, which is a grammar of data manipulation. How do I consistently manipulate my data? ggplot2, which is Wickham's little pet project, is a grammar of graphics. How do I do graphics in a consistent fashion so I don't have to sweat the details? Tibble is a re-imaging of data table. They just realized that the data table had some deficiencies, and so they redefined how they do data tables to be consistent with their vision. Reader, how do I read in rectangular data? TidyR, standard data storage format, and then is there a way of making this even more functional in nature? Because the hybrid between functional and imperative programming, they want to push you more and more towards a functional programming approach. And some additional capabilities. And this is one thing that Bob Schumacher was very committed to. He always talked about Sweeve, and Sweeve was a method of writing a LaTeX document that had our code embedded in it. If you ran that code through Sweeve, Sweeve would identify the sections of our code, call R, do the data analysis. Any results from that analysis would be put back into the LaTeX document, and you could do what is essentially called literate programming. When you're doing MATLAB, you kind of self-document as you type through, correct? The idea behind Sweeve and its successor Knitter is that you can essentially write a LaTeX document, insert your code in, and then now you have a set definition of document, and then you could run it. It would self-document, fill in all the graphics appropriately. In fact, Bob Schumacher mentioned that back, I can't remember what they were doing some study on, and he was on a university committee, and they found that when they walked into the meeting, that they apologized, said, well, we'll probably have to put this meeting off because the data we sent you was wrong. It really should have been this data. And so Bob says, well, hold on a minute, give me the data. And he put the new data in. He already had his Sweeve document in place and just had it recompile, and within probably about 10 minutes, he had a whole new documentation set based on the new data, instead of having to go back, reschedule, and maybe in most methods, regenerate every single plot independently and then reassemble a new document. Literate programming. There's also something called Shiny. It's a web-based interface, and it lets you build dashboards for the web. This is contingent on the existence of RStudio running a server in the background. You do calls to RStudio on the server, but if you follow the Shiny template, you can develop a dashboard where there's a certain data set. You can now play with the data in the web on this particular data set and see how it morphs and transmutes based on your definitions of how you're modeling it. And there is a list of sources. There's an introduction to R. If you're brand new to R and you just want to read through a consistent presentation that is more thorough than what I've done, read the intro to R. There's an R FAQ out there. There's also other documentation. This is where that bioinformatics and spatial analysis stuff shows up. There is a journal, and I think it is a semi-annual journal that people will submit work that they have done using R, describing not just the data work they're doing, but how they implemented different features or packages in R to accomplish that. And so if you're looking for some significant work that people have done, that's a good place to turn. There's a wiki out there. There's also a blog site that again has lots of contributed articles. If you're looking for something to, how do you do this particular thing, you go to R bloggers and see if somebody has already done it for you ahead of time. There's an R gallery out there, again, to see visually what types of visual presentations people have been able to put together with R. And there is also Stack Exchange. If you do Stack Exchange, there is a large body of information on how to solve different R problems from that Stack Exchange. And that is my presentation. So any questions before I actually switch over to my laptop and show just dynamically some things that I do with R? And then after that, it'll be essentially workshop time that if you want to install or ask questions, mill around, I'll hang around as long as you're trying to do stuff, okay? So any questions before I somewhat show dynamically some things with R? You don't know what to ask, right? So let's switch over to the laptop and wake the laptop up. Wake the laptop up. And wake it up. And that's not a good sign. It's sitting here idle for a while. Here, I think we got something, and it's going to come through. There we go. So, the first interface, this is the R GUI. If I go to the console, notice I have a number of app options here. Here's my help. I could click on here and bring up the FAQ on R. FAQ on R for Windows. There are a number of manuals here. If you want the full reference, or if you want some sub-areas that R has documentation on, you can click on here. If you want to go to the CRAN homepage, it'll bring up your web browser so you can get to that location. If you want to install a package, you can first of all choose your mirror site. And now you can scroll through. Now this particular list is somewhat limited. It does not have the Wright State website here, but you can choose any one of these in the United States and it would serve as your package server. And then once you have chosen a particular location, you can choose install packages. And now it brings up a list of all the different packages that exist in R. And this is just the ones that are through CRAN. There are also some packages that have been kept on private sites or on proprietary sites that you can still access, but these are the ones that are publicly submitted to CRAN. And then just to see a little bit of work here, I had written a program here to essentially do an ordinary differential equation solver, or actually use a package that involves it. Whenever you start up a package, you have to, first of all, install the package, and then you use a command called library. So in this particular one, I bring up library dsolve. It will load the package in. Once the package is loaded in, I can now access functionality within that package. And to run a particular line of code, you just do Control-R, and you can sequentially work your way through. And right now it looks like it's not too happy with some things I've done here. If you want to do things quickly, you can do Control-A, which selects everything, and then Control-R runs everything. And this was that nonlinear oscillator that I had mentioned before, and this is the script that goes with it. On the other hand, if I want to do not the R GUI, but I want to do RStudio. I could have my list of my files in my directory. I could change my directory. Somebody mentioned the idea of, do I have to be in a particular directory? You can move around here, find the directory you want to operate in, and then you can set it as your working directory. It's a little bit more clunky in the R GUI. It's a little bit more elegant in RStudio. Plots, of course, packages. These are the packages I currently have installed in my machine. It looks like a lot, but it's really not. Here's the data from doing some kind of a run. And I'm going to install Rattle. Now I've already, first of all, I have to do library, Rattle. And now that it's loaded in, I can do Rattle, open close parenthesis, and it should bring up a new interface. And supposedly it's somewhere. Did it show up? Oh, it fell behind my window. So here's Rattle. Now if I don't have any data to work with right now, just come over here and hit execute. It's going to bring up a window and it's going to ask me, no file name has been provided. We require a data set to be loaded. Would you like to use our example weather data set? So just tell it yes. Now here's that data. Location, minimum temperature, max temperature. If you work your way all the way down, is there going to be rain tomorrow? Notice it's going to identify, first of all, import values. Your target would be what you're trying to predict. You could, now I'm not sure, I've not looked at the risk parameter here, but you could ignore certain factors. You really don't want to do analysis on those. You could drop those out. You could also change weightings on different factors. So let's just drop off some stuff here. Let's ignore rain today. Let's ignore humidity measurements. Let's ignore the wind direction and the wind speed and the wind gust direction. And let's see, this still leaves me with quite a few numbers. Hit execute again so that it recognizes what parameters I've changed. If you change parameters and move to a new window, it's not going to register what you've changed and it's going to use the previous values. But once you do execute, it's going to be sitting there. Let's see, we have, let's see. How about, one other thing to keep track here is, it tells me, comments here, it tells me there's some missing data. There's 3 missing data values. There's 114 data values in that particular parameter or that particular factor that I'm working with. Let's go over to the, let's see, how about explore data? I could do distributions. So we could do maybe a histogram of the max temperature against the outcome, which is it going to rain tomorrow or not? Hit execute. And let's see, max temperature, I was expecting, the reason I'm not seeing anything over here is I don't have plots. There we go. And so it uses whatever function, or I should say whatever platform you called Rattle within, it's going to use its graphics capabilities. And in the plotting region, here is the probability of rain tomorrow, no rain, versus yes rain. And then the temperature going between something probably about 8 degrees up to about 34 degrees. This would be, I'd assume, Celsius scale. But you could visually look through and say, this might be a good factor at distinguishing whether I can make a prediction of rain or not, because there's separation between the no and the yes value. And you could work through and then choose maybe a different parameter. Let's look at sunshine, execute. And now, if there's a lot of sunshine, no rain tomorrow. If there's not much sunshine, yes rain tomorrow. You could also do a correlation. And then notice that correlation matrix I mentioned before that show me which parameters are well related to each other, maybe those that are anti-related or anti-correlated with each other. You could come up here to clustering, or you could model. You could choose, let's say, some kind of a forest, execute, and then it's going to come through and try developing or looking at the relationship between yes and no for my different factors. And ultimately, you're trying to develop either a decision tree as to, do I look for this value first and then this value, and then work my way through to predict if there's rain tomorrow or not. You could also do neural net, and it will then generate certain hidden values of your network. There's a certain default value, but you could tweak it. And then if you wanted to see where the results are, you could hit log, and this is just an ongoing log of everything I did since starting up Rattle. And let's see, is there anything else I wanted to show you? Probably one last thing is, let's switch back here. Let's go to CRAN. CRAN, scroll down here, United States, and right about, let's see, where's right, there's right state. IIS.stat right edu CRAN. If you want to load in the package, you could do load Linux or load R for Linux, for Mac OS, or OS X, or for Windows. The current version, you could load in the base value, which is 3.4.2. And then once you've installed that, you could then access different packages. Come down here to hit packages. You can either list the packages by date of publication or sorted by name. And then once again, you have this nice extensive list here. If you're interested in neural nets, neural net, neural, and then there's the documentation. And the documentation would give you a listing of, now in this case, it looks like this is a data set for neural nets. Let's go back to this one here. The documentation would give you a list of all the different functions that are within the package and then how to use it. So, questions on R? If you have your laptop and you want to load R and you want to see if you can kind of get some of this stuff up and going yourself, you're welcome to do that, and I will help get you past any hiccups. So I guess at this point, if there are no questions, we're done with the seminar part, and we'll just transition into the workshop part. And I will also take questions, not just helping people get stuff to solve, but if you have just general other questions, I'm available, and I probably will stick around for about a half hour or more, depending on how long you need. Yes?
I did notice you put like a variable as like a function, parentheses, and then you generated your vector inside of that. Why did you do that? Because I just tried it, and you can just put like, to make 1 to A,
yes,
you just do A is equal to 1:8.
And I think I wiped this out, but if I want a list, there are lots of ways to generate a list.
Right.
One way of generating a list is that.
Right. Yeah.
Another way of generating a list is that.
Right. And the
Another
same thing,
one is SEQ, and then I think I can do 100 values, and then something like increment by 1.
so it's like a sequence, just start from.
Yeah, and so then the
And-
sequence, you could define your starting value, 100 increment by, and I can't remember what the 3 parameters are, but one would be your starting value, one your ending value, and then how many values in between.
Right. There's a similar function in Python like that.
Yeah, so you can do it, this is clean. I just, in my example, wanted you to realize you can make collections.
Okay.
And collections, you could define them individually or as an array, but this will do the same thing. Good question. Other questions? Well, thank you for coming.